So organic chemistry is defined as the study of compounds containing carbon, and most substances in the world belong to this class. Food, drugs, wood products, paper products, clothing, the grass outside, anything biologically related is made up of organic molecules. Most of our body, except for our bones, are made up of organic molecules. So just about anything that we generally come into contact with, except for metals, glass, ceramics, would be considered organic compounds. Hydrocarbons, as we briefly discussed in a previous chapter, are molecules that contain only C's and H's, only carbon and hydrogen. Other classes of organic compounds might have heteroatoms, which are defined in organic chemistry as any atom other than carbon and hydrogen. So oxygen, nitrogen, sulfur are all common heteroatoms in organic chemistry. Remember that covalent bonds contain a shared pair of electrons. Here's a covalent bond, the CH bond in methane. That's a shared pair of electrons. The carbon shares it with the hydrogen. And covalent bonds can be polar or nonpolar. In this case, they are nonpolar because we define carbon and hydrogen to have equivalent electronegativities. Also remember the like dissolves like rule. Polar compounds dissolve in polar solvents, like salt dissolves in water. Both are polar compounds. Nonpolar compounds dissolve in nonpolar solvents. So compounds derived from oil will dissolve in other compounds derived from oil. Remember the molecular structure. This carbon with four atoms around it is a tetrahedral carbon. The carbons here with this double bond have only 3 atom groups around it, and it is a planar carbon. This is a trigonal planar geometry around this leftmost carbon, 3 atomic groups. This leftmost carbon has only 2 groups surrounding it, an H and a triple bond to C on the other side. So this carbon is linear. And these are 3 geometries that we will come into contact with many times in organic chemistry. Section 6.1 will deal with hydrocarbons. And there are a few different types of hydrocarbons. There are those that are called saturated hydrocarbons. These are called alkanes, and they have all carbon-carbon and carbon-hydrogen single bonds. So these carbons are all tetrahedral in their molecular geometry. And so the bond angle anywhere in this molecule is 109.5. And we can have any number of carbons, and as we'll see in a few slides, there's a certain number of hydrogens that can correspond for any combination of carbons. A second class of hydrocarbons are called alkenes. These have at least one carbon-carbon double bond shown here. And around the double bond, the angle is 120, as this carbon is trigonal planar molecular geometry because it only has 3 atomic groups surrounding it. We can also have alkynes, which deal with or possess a carbon-carbon triple bond. These are linear around the carbon-carbon triple bond because the carbon has linear geometry because it only has 2 molecular groups or atomic groups surrounding it. And so the bond angle here is 180 degrees. And a fourth class, called aromatic, are those hydrocarbons that have this structure. And we'll talk more about this structure later on in the chapter. Essentially, it has a ring, a 6-membered ring, and 3 double bonds in it. So alkanes are often called saturated hydrocarbons. That means they have the most hydrogens possible for a given number of carbons. And so a saturated hydrocarbon has this general formula, CnH2n plus 2. So for a given n, we can solve and determine the total number of hydrogens possible for that n. For example, ethane here, C2H6, if n equals 2, the H count is 2 times 2 plus 2 is 6. So C2H6 corresponds to a saturated hydrocarbon chemical formula. Unsaturated hydrocarbons contain fewer hydrogens for each C. And so if we were to take a formula, say C2H2, we can certainly determine that it does not fit this formula. If C is 2 and the H is 2, it doesn't fit 2n plus 2. So that would be considered an unsaturated hydrocarbon. Alkenes, alkynes, and aromatic compounds all fall in the class of unsaturated hydrocarbons. So here is C2H4, that's ethene or ethylene, and that certainly doesn't fit the CnH2n plus 2. Acetylene, the simplest alkyne, C2H2, does not fit the saturated formula, and an aromatic compound, C6H6, also does not fit CnH2n plus 2. So some practice problems. Which of these here are saturated hydrocarbons? Oops. Okay. So which of the following are saturated hydrocarbons? Remember that we want to have CnH2n plus 2. So if we start with 7 as N, 2 times 7 plus 2 equals 16. So that would be the hydrogen count if this were a saturated hydrocarbon. Right? 16 hydrogens. And we see here there are only 14 hydrogens, and so this one is called unsaturated. C6H14. If N equals 6, 2 times 6 plus 2. 2 times 6 is 12, plus 2 is 14. So this indeed is saturated. And sometimes we'll abbreviate saturated just SAT period. C3H8. N equals 3. 2 times 3 plus 2. 6 plus 2 is 8, so this one is also saturated. C2H2, if N equals 2, 2 times 2 plus 2 equals 6, and we have only 2 hydrogens, so this is an unsaturated compound. So here we can see how to use the general formula of saturated hydrocarbon to determine, just by giving the chemical formula, which are saturated and which are unsaturated. Second question, how many covalent bonds does a carbon atom in a molecule contain? So carbon is in group 4A, right? So it has 4 valence electrons, and that means that it forms 4 bonds. And so the carbon, every carbon that we're going to draw in organic molecules should have 4 bonds. If your carbons don't have 4 bonds, you did something wrong. And this could be a single and a triple bond. That adds up to 4. 2 times double. 2 times single and a double. So any combination can add up to 4 bonds, not 5 and not 3. So the carbon will always have 4 bonds, and that's because it has 4 valence electrons, and it needs 4 more electrons in order to have a complete octet. And it can get that by sharing 4 bonds with other atoms. Clicker question 6.1. This one could have been answered in previous chapters when we discussed molecular geometry. What is the bond angle on a tetrahedral carbon, such as the one shown here in methane? So here we need to remember the bond angle for tetrahedral atoms. It doesn't really matter that it's carbon in methane, just that it's a tetrahedral molecular geometry. And so that bond angle, of course, is 109.5. So physical properties of hydrocarbons. The carbon-carbon bond certainly is nonpolar. It's 2 atoms of the same electronegativity. Carbon-hydrogen bonds we define as also nonpolar. Carbon and hydrogen are close enough in electronegativity that they essentially are nonpolar bonds. And so anything composed only of C's and H's is a nonpolar molecule. And that means that hydrocarbons only interact weakly. They don't have dipole moments or dipole-dipole interactions. They certainly don't have hydrogen bonding. And so they have low boiling points, meaning it's easy to change them from the liquid phase to the gas phase. There's not very much there's not a lot of intermolecular forces to overcome, only the dispersion forces. And because they're nonpolar, they are insoluble in water. So we know that oil and water don't mix, while hydrocarbons essentially are a form of oil. And so this leads to a couple definitions. Hydrophobic compounds are those that don't dissolve in water. They're considered to be water-fearing. That's essentially what hydrophobic means. So they're nonpolar, they're hydrocarbons. They might dissolve in other hydrophobic materials such as other hydrocarbons, right? So methane or petroleum products might dissolve in paint thinner, for example, or other types of oil. Hydrophilic compounds, on the other hand, are those that are polar. They dissolve in water and they're water-loving. So here's a drawing of ethanol. That has an OH bond right here. We know that it's polar. It has hydrogen bonding, so it will dissolve in water. It is a hydrophilic compound. So based on your everyday experience, which of the following household substances are hydrophobic? Which of these are water-fearing? Well, orange juice, we know, is derived from oranges, and oranges have some liquid in them, that's water. We could pour some water in the orange juice, it will mix together. We can use water to wipe our face off if we spill orange juice on it. And so orange juice would be a hydrophilic substance, a water-loving substance. Motor oil, on the other hand, it has oil in the name. We know that that does not mix with water. If we spill some motor oil on the ground, we can't just flush it away with water. It will float on the surface of the water. So this is a hydrophobic compound. Sugar, I think we've all experienced dissolving sugar in water. It makes a homogeneous solution. Sugar is polar. We'll talk more about sugar in the later chapters of the book. So that is a polar substance. It's hydrophilic. It is not water-fearing. Tanning lotion, it feels oily. Some of them are made to be waterproof, so they don't dissolve in water, and that would be a hydrophobic compound. So tanning lotion is also hydrophobic. The next question says, why are hydrocarbons nonpolar? Explain why in terms of electronegativity. And this again goes back to the definition of carbon and hydrogen having the same electronegativity. So there's no difference between the two. That means their bonds cannot be polar. So a carbon-hydrogen bond or a carbon-carbon bond is nonpolar, and those are the only bonds we'll find in a hydrocarbon. So because of the equal electronegativity of carbons and hydrogens, we have nonpolar molecules when we make a molecule composed only of C and H. Section 6.2, going to deal with saturated hydrocarbons, the alkanes. So the alkane structure, remember that there are no double bonds in an alkane. All carbon-carbon bonds are single, and the remaining bonds are between carbon and hydrogen. Each carbon, of course, shows tetrahedral geometry because it has 4 electron groups around it. And alkanes with more than 3 carbons are zigzag chains. So here's a 3-carbon alkane called propane, and because of that tetrahedral geometry, we can see that this adopts a brief zigzag chain. If we made a longer model, we'd see a much greater zigzag here. So a carbon-carbon bond has rapid rotation at room temperature. And when the bonds are rotated, we get different conformations. So different conformations are the same compound. They have identical physical and chemical properties. They're just drawn a little differently. So here we have 5 carbons in a chain. We can see the zigzag chain. And each carbon has its maximum amount of hydrogens. The 2 on the end have 3 hydrogens attached. The 3 carbons in the middle have 2 hydrogens attached because they already have 2 neighboring carbons. So each carbon has 4 bonds to it. If we rotate around this bond indicated with the red sort of circular arrow, we rotate this carbon up and we get this conformation. We have not changed the molecule. We still have 5 carbons in a chain. We've just changed it to a different conformation. That's because we've rotated around this single bond. And they have the same physical and chemical properties. So this molecule is called pentane. It has 5 carbons and 12 hydrogens. I want to take this opportunity to show the in the ebook, when you're reading through the ebook, if you have access to that, you'll read about alkane conformations, which we just started, and you can click on the virtual model toolkit. There's a lot of these in this organic chemistry chapter, and that will bring up a window that looks like this, where you can take hydrogens, carbons, oxygens, nitrogens, chlorines, single, double, triple bonds, and essentially make a model. All right, I've started this one. It takes a little time to drag all the hydrogens over and the carbons, but essentially you drag them over to the template, and eventually we're able to produce a model of pentane. And this is a way to make a model without having a model kit in front of you. And so I encourage you to use any opportunity with this virtual model toolkit. So once we've produced pentane, the computer will draw it in a zigzag chain, and it will allow you to rotate it and see how the atoms are lined up. Each carbon here has tetrahedral geometry. Again, the N2 carbons have 3 hydrogens attached, the middle 3 have 2, and you can rotate it as much as you want. And then when we continue, go to the next page, it will take us to some pentane conformations. So here we can look at the different pentane conformations, and it'll say click on the highlighted conformations of the pentane molecule to examine other typical conformations. So I'll just do one, I'll let you do the others on your own, but if we click on this highlighted portion, it will rotate it around the single bond for us to show a different conformation. And then again, we can rotate that and see that these are different conformations. They're still the same molecule. We haven't broken any bonds, we've just rotated around a single bond. And so I encourage you, whenever you see the virtual model toolkit, to take a look at that and gain some more insight into these hydrocarbons. This toolkit can allow us to visualize in a bit more 3 dimensions, more than we can visualize on paper. If you do happen to have a model kit, I encourage you to use that to make models of any drawing we see in the book, and then you can look at it in 3 dimensions. So again, we can rotate around carbon-carbon single bonds to make a new conformation. The same compound, just a different conformation. Clicker question 6.2. All alkanes follow which pattern? Okay, so remembering from the first section, the formula for an alkane is CnH2n plus 2. So A is the best answer here. It indicates the formula for an alkane given a certain number of carbon atoms. Structural isomers now. Structural isomers have the same formula, but they have a different connectivity among the atoms. That means we have to break bonds and reform them in other locations in order to go between 2 different structural isomers. So they are different substances. Whereas a conformation is the same substance, it's just rotated around some single bonds. So here's some examples. Here we have C5H12, that fits the formula for a saturated hydrocarbon. The most basic structure of that is 5 carbons in a row, all with their maximum number of hydrogen atoms. We can look at the space filling model and the ball and stick model. This is what we just looked at in the virtual model toolkit. Now, if we were to take this last carbon off, break this single bond, and attach it to the second carbon from the end, we would end up with this structure. Here we have 4 carbons in a row, and the second carbon in has a branch. Right? So we've broken a bond in order to make this branched structure. We had to break this bond and make a new carbon-carbon bond right here. And again, the space-filling model looks a little different, and certainly the ball and stick model also looks a little different. So this is a structural isomer. It's a different compound. As we can see here, it has a different boiling point because it has a different shape. So different compounds will have different physical properties. And if we were to detach another carbon and attach it to the second carbon in, we make essentially a plus molecule. 3 carbons across and a branched carbon in the middle that has both a carbon on top and a carbon on the bottom. The space-filling model is much more compact. Here's the ball and stick model, and we can see that the boiling point has dramatically decreased to 9.5 degrees Celsius. And now the only difference between these 3 models is simply their shape. They all have the same number of carbons, they have the same number of hydrogens. So they have the same mass, they have the same amount of electrons, they have essentially the same amount of dispersion forces, except that a linear molecule can come into contact with another linear molecule, much like 2 baseball bats or 2 pens lying side by side, and they have a lot of surface area that can be in contact with the other molecule. And so dispersion forces will have a greater effect in that case. Whereas this model, we can see that its space-filling model looks much more compact, almost like your fist or a baseball. And 2 baseballs can come into contact on a very small portion of their surface. right? As opposed to baseball bats, which would have a long portion of contact between them. So this would have a small portion of contact between other molecules of itself. This is called a neopentane. And so because there would be decreased contact and decreased interaction, dispersion forces would have a less effect on holding the molecules together, and so it would be easier to boil them. The boiling point is lower. So here's a question about structural isomers. Which of these three choices are structural isomers? And so in deciding a structural isomer, we have to identify that pair which would have to break bonds in order to go between the two molecules in the pair. So this first structure here has 4 carbons in a chain. This structure here looks different, but I think we'll agree after inspection it also has 4 carbons in a chain. And so even though they're different arrangement of that chain, it's still 1, 2, 3, 4 in a single chain. These are the same structure, just a different way of drawing it. For part B, 1, 2, 3, 4, 5, 6. 6 carbons in a chain. This molecule also has 6 carbons in a chain, same number of hydrogens, so it is also an identical structure, just drawn a little differently. We've just rotated around a couple of carbon-carbon single bonds. For the final choice, 1, 2, 3, 4, 5, 6, again 6 carbons in a chain, but now we have 1, 2, 3, 4 carbons in a chain with 2 branch points. So we've broken some carbon-carbon bonds, reformed them in other locations, giving structural isomers in part C. This has different connectivity than the first straight chain isomer is how it's called. This is the branched chain isomer. So we've broken chemical bonds in order to produce this structure using the same number of carbons and hydrogens. So cycloalkanes then are a ring created when a carbon-carbon bond is formed between two ends of the chain. Here example is pentane. If we remove these two H's from the either end of the chain, we can connect those two carbons if we pull the chain around in a ring. And so we can create a new carbon-carbon bond. We now have 2, 4, 6, 8, 10 hydrogens, where we had 5, 5, and 2, we had 12 hydrogens to begin with. If we remove 2, make a new carbon-carbon bond between the ends of the chain, we can make a ring. And chemists like to draw them even more simply. We just draw this pentagon. That stands for all of these different carbons and hydrogens and bonds. And so cycloalkanes can be written as polygons with 3 or more sides. There's a carbon present at each corner of the polygon, and we imply that 2 hydrogens are attached every time there's a corner. So here's cyclopropane. It's a 3-carbon alkane, a cycloalkane. There's a carbon here, here, and here. And if we observe that this carbon has 2 bonds to it, each of these lines is a bond, it needs 2 more bonds to have its full octet. We always want carbon to have 4 bonds. And so this corner here implies 2 H's attached to the carbon, 2 H's attached to the carbon, and 2 H's attached to this carbon. So every time we see a point with 2 lines emanating from it, that means there are 2 additional hydrogens attached that we don't bother to draw in. Cyclobutane, same way, except there are 4 carbons in the cycloalkane. Cyclopentane, again identical, there are 5 carbons in the cycloalkane here. And again, each corner has a carbon with 2 hydrogens attached to it. Cyclohexane is one of the most common ring sizes. Another common size is the 5-membered ring. So most rings that we see in nature are these 5- and 6-membered varieties. And cyclohexane, C6H12, is not flat. So here we see the ball and stick and the tube model. The carbons are at these intersections here. And we can see that they kind of go up and down and up and down and up and down. And so we can see this almost looks like kind of a crown with some points pointed upwards and points pointed downwards. But these 6 carbons are not in the same plane. So let's look at these practice problems here. Do different conformations represent different compounds? So different conformations. Remember that a conformation has same connectivity. Just rotated C-C single bonds. And so they have the same connectivity. They don't represent different compounds. If they were different compounds, they'd have to have a different connection between the atoms. And since it's just a conformation, we've just rotated a few bonds. They have the same connectivity. They are the same compound. Next question. Write the structural formula for the two structural isomers of C4H10. So now structural formula, that's going to have different connectivities. The first structural formula we want to show would be the most basic one. We'll draw all the carbons in a straight chain, and we'll fill in with hydrogens. So this carbon has one bond. We need to add 3 more hydrogens to it. This carbon has 2 bonds, so we need to add 2 more hydrogens to give it 4. Whoops. Same with this one, 2 more hydrogens. And this one, this last carbon, has only 1 bond to start with. We add 3 more to give it 4 total. And we wanted 10 hydrogens. 4, 4, and 2 makes 10. So how do we make this into a different structure? Well, we have to break a bond and reform it somewhere else. And so most of the time the easiest bond to break is one of these N bonds. So let's break that bond. We now have 3 carbons in a row. And I have a 4th carbon here that I want to attach somewhere to make a new structure. If I attach it here, that doesn't give me a new structure. I still will have 4 carbons in a row. Same thing with attaching it to the first carbon. I would still have 4 carbons in a chain if I attach it to either of these N carbons. So that leaves the middle carbon here. You can see now that I have a new carbon structure. I have 3 carbons in a chain. The middle carbon has a new carbon attachment. And now I need to fill in hydrogens. This carbon needs 3. This carbon needs 3. And this, the carbon in the middle already had 3 carbon neighbors, so it gets 1 more hydrogen. And the carbon on the right also needs 3 more hydrogens. And let's confirm that we have the correct number of hydrogens. We have 3 on this carbon, 3 on this carbon to make 6, 3 more over here to make 9, and 1 more is 10. So we have the same formula for both of these drawings. We just have a different connectivity, and those are, by definition, structural isomers. So we're going to refer to this tube model of the 6-membered cycloalkane, cyclohexane. How many hydrogen atoms are in each carbon atom? So remember that a carbon atom is right here, and there's 6 of them, 1, 2, 3, 4, 5, 6. And carbon atoms are in black, hydrogen atoms are in gray on this drawing, and so we can see that there are 2 hydrogen atoms for each carbon atom. 2 hydrogens on each carbon. The next question is, are all the carbon-carbon bonds in the same plane? And as I said before, we have some carbons pointing sort of in an up direction, some pointing in a down direction. So these bonds will not all be in the same plane. They're in different planes. Next question, are the CH bonds all in the same plane? Well, this one's sort of pointing down. This one's sort of pointing that way. And this one's pointing up. So we can see that we have 3 or 4 different types of CH bonds. They're not all in the same plane. And the model is not flat. We can see that from this tube model here. It does not appear to be flat. If you make the model with your virtual model toolkit, it can rotate it and show you that the molecule is not flat.